So this is joint work with collaborators at Brown. In a software-defined network, there are two key components. There's a controller program that dictates forwarding behavior and a collection of switches that implements that behavior. While the switches understand really a very simple set of match action rules, the controller program can be written in an arbitrary programming language. And just like most arbitrary programs, controller programs usually have state. This means that when you're programming a software-defined network application, really you're creating a three-tier application because you have some sort of data store, some control logic, and the flow table rules living on your switches. This is not dissimilar to the three-tier architecture we see in web programming, where there's a database and a client tier and a server tier. The key difference here is that the limited expressivity of the rules that live on the switches force a really sharp distinction between what can be handled on the switches themselves and what really must be sent up to the controller for handling there. This means that when you write these programs, you're writing really a meta program that's constantly reevaluating its internal state, issuing new flow table rules, responding to packets to update its state, and so on. Let me give you an example of what I'm talking about. This is a NAT application written for POX. It's got a lot of different things that it has to do. It has to explicitly respond to packets arriving from the switches. It has to also reply to those packets, to the switches, telling the switches how to forward packets, how to translate packets. It has an internal state, keeping track of all of the NAT flows and what ports are being used for them. It's got to update that. And it's got to install rules on the switches to, well, first, make sure that future packets in the same flow don't get sent up. And it's also got to make sure it continues to receive fresh packets in new flows so it can update its state and issue new flow table rules. But doing this is easy to get wrong. Why? Because there's this implicit dependency between the state and the flow table rules. The state influences what rules go onto the switches, and in turn the switches influence what is in the state, and that influences what rules go up onto the switches. This leads to bugs, a few standard bugs. The first, maybe the most obvious, is that you can get an inconsistency in the forwarding state being held on the switches versus the forwarding state held on the controller. The second is that the switch might neglect to download install appropriate rules saying, please tell me about these packets so that I can keep my state up to date. And the switches might end up doing the opposite thing as well. They might send too many packets up to the controller, right? And that makes the controller take longer to respond. It causes more latency, bad network performance. Something more high level here as well. SDNs are supposed to allow us to write programs for our networks. And when you write a program, you'd really like to verify that it does certain things, that there's program correctness properties that hold. Verifying languages like Java and Python is really an heroic effort. And it's worse in this case because you don't just have to verify a program, you have to verify a program that contains a little compiler inside that's issuing rules in a completely different abstraction. And so you have to verify across these multiple tiers. So to address this problem, we've been working on a language called Flowlog. Flowlog is what we call tierless. What does that mean? It means that the runtime handles installation of flow table rules for the programmer. Not just rules to represent forwarding behavior, but rules necessary to keep the state consistent. That lets the programmer focus on the behavior that they want rather than on this bookkeeping with flow table rules. Flowlog's also interesting because we have built-in verification support that works across multiple tiers, and we'll talk some more about that later. As we step through Flowlog, you may notice the syntax is slightly reminiscent of SQL, and it'll be useful to keep databases and SQL in mind as we go through the examples. Just for illustrative purposes, I'd like to show you a NAT written in Flowlog. I'm going to focus just on the outgoing direction and only on a situation where there's one switch with two interfaces, an internal and an external. So like I told you, state in Flowlog Flowlog resembles SQL, and so state is correspondingly relational. This declaration says there's a table called NAT. It's got 4 columns. The first 3 columns store the layer 2, 3, and 4 source, pre-NAT, and the 4th column stores the port that's being used for multiplexing. Flowlog also has variables. This variable holds exactly what you imagine it does, the next available port, starting at 10,000. When we're writing an application to do outgoing NAT, there's 2 cases that we have to deal with. We've got to deal with a packet arriving that's part of an existing flow, and we've got to deal with a packet arriving that's the first packet in a new flow. And I'd like to address these separately. So first, we can tell Flowlog, when you receive a TCP packet, call it P, arriving at interface 1, the internal port, where there exists a row in the NAT table with the first 3 columns corresponding to the source address of the packet, and the 4th column storing the NAT port to use, do something. The second possibility, new flows, is very similar. When a TCP packet arrives at the internal port, but there isn't anything in the table to use, do something else. Now for functionality, right? Back to the existing flow. All we want to do is forward that packet as a new packet that's coming out port 2, the external port, that's had its layer 2 and 3 address rewritten to the addresses of the NIC, and has its layer 4 port set to the NAT port value that we obtained from the table. There's a very similar forwarding rule used in the other case. The difference here is that we don't get a port to use from the NAT table, we just get it from the next port variable. Since this is a fresh flow, there's a little extra bookkeeping that we have to do, right? We'd better insert a row into the NAT table. And since now we've used the current value of next port, we have to increment next port. And really, that's it for outgoing NAT. There's nothing here talking about installing OpenFlow rules. There's nothing here about maintaining state on the controller, about when the NAT table gets updated, about what packets have to go up, about what packets don't. The runtime handles all of that for us. But that's just packet forwarding, right? You can do more than just packet handling in Flowlog. The 3-tier diagram I showed you earlier is kind of an oversimplification, right? Because programs don't exist in a vacuum. There may be other applications that we want to provide Northbound APIs to, right? Yes, you can do that in Flowlog, and now I want to give you another example to show you how. Suppose that you maintain a campus network. I know some of you here may do just that. And you provide connectivity to many, many laptops that your students own. Unfortunately, somebody may come along and steal one of the laptops. You'd really like campus police, when that theft is reported, to be able to tell the controller, here's a MAC address of a stolen laptop, please watch for these laptops. If you see somebody using it, report their current location, report the current time, so that we can go and track them down and recover that property, right? There's 3 pieces of the Flowlog program necessary to implement this. The first is the Northbound API, so that the police can actually communicate to the controller program. We handle these with thrift in Flowlog in the form of event declarations. The first 2 events are pretty simple. They are reports from the police, a stolen laptop report containing the MAC address of the stolen laptop, and a stolen laptop cancel containing a MAC address as well, saying that we have recovered this laptop, please stop sending us notifications that you've seen it. The third event is meant to be sent up to the police, saying, we have found this laptop, here's its MAC address, here's the switch ID where it's been seen, and here's the current time. In Flowlog, when you're sending an event up via an API, you need to declare a named pipe that says where to send the event. Here, this pipe just is called notify police, and it sends stolen laptop found events up to the appropriate location on the network. In this case, it's just localhost. Just like events give you asynchronous communication with a Flowlog controller, Flowlog lets you define remote tables so that you can synchronously access state that's provided by other processes that may not even be running Flowlog. This declaration sets up a remote table called getTime. We'll use it just like an ordinary state table that accesses a timing server and obtains the standard second since epoch and updates every second. And now for the rules. The table is exactly what you expect it is. It stores the stolen MAC addresses. There are two rules to respond to the two events that the controller can send. One to deal with cancellations that removes stolen laptops from the table, and one for reports that adds stolen laptops to the table. And finally, there's a rule that responds to packets from stolen laptop MAC addresses that appear on edge ports in the network. When those packets are seen, Flowlog constructs a stolen laptop found event, sends it out that named pipe that we declared, and the police see it and hopefully go and recover the laptop. Again, that's it. The marshalling has been handled all by Flowlog. There's no RPC wrangling that the programmer has to do. There's no worry that a packet is not going to be sent up to the controller to result in an event being sent. All of that is handled by the runtime for the programmer. So you've just written a program. You'd really like to know that certain things hold of it. For instance, in this case, a simple property might be, well, only the stolen laptop cancel event sent by the police can ever remove a MAC address from that stolen table. Right? This property looks kind of simple. In the example that I just showed you, it's kind of obvious from inspection, right? But the point is that even as your system evolves, provided your API remains the same, this property can be reused over and over and over again. And indeed, you can write properties like this for much more complicated systems. So how do we do program verification in Flowlog? Well, we take advantage of the fact that Flowlog programs are designed to be equivalent to formulas in first-order logic, which means we can automatically translate them to Alloy, which is a program verification tool. Here's an example of this property written in Alloy's assertion language. It's fairly concise. When you feed the program plus this property to Alloy, Alloy will reply saying no counterexample is found, and it replies in this case fairly quickly, in about 1/10 of a second. What if the property doesn't hold? Well, if there's a bug in the program, or in this case, if we have changed the property so that it doesn't hold, and we pass that to Alloy, Alloy will say, yes, a counterexample has been found, and then it displays that counterexample graphically and concisely in a way that can really help the programmer zero in on where their bug is located. This is one of the reasons that we used Alloy in the first place, is this output. Let's take another look at the original property, though. There's something interesting going on here. It's actually talking about a relationship between multiple things. It's talking about a relationship between multiple tiers of the program. It's saying that the database can be affected in a certain way by events from the control program and by exclusion by packets arriving on the network. This is not uncommon. This is very common. Often when you want to verify an SDN program, you want to verify that packet arrivals can affect the state only in a certain way, or packet arrivals must affect the state in a certain way. Because Flowlog is tierless, the abstraction over which this verification is performed is also tierless. This means that these properties that we write about the behavior of Flowlog programs don't need to talk about open flow rules. They don't need to talk about what packets go to the controller. They only need to talk about what packets appear on the network. This, we found, really makes writing properties simpler. It makes the verification process simpler. And that means that the verifier is easier to use when you're developing new software for your network. Indeed, we found it very useful. Well, as Andrew keeps reminding me, this is a systems conference. So although I've told you about our verification in brief, I really want to tell you about how Flowlog responds to events that appear on the network and how the system works. When an event arrives, it gets converted to a row in a temporary database table. Then we use the XSB Prolog engine to evaluate the program with respect to the current state and that arriving event in the temporary table. That tells us how to send output, either via the netcore library or via thrift, and how to update the controller state into a new state. Deletes first, then inserts. Now, so far, it looks kind of like everything has to go to the controller, and in a real system, that's kind of a non-starter. So yes, we do have a method of producing open flow rules automatically, as I've been saying. How do we do that? Well, we use an idea called proactive compilation, and proactive compilation does this. The controller produces a global forwarding policy. The proactive compiler takes that policy and pushes it down to all of the switches automatically without waiting for any packets to arrive and trigger the installation of those flow rules. What we've done here that's novel is add state into the equation. Not only might you have a Flowlog rule that describes forwarding behavior involving state tables, but if you have insert and delete rules in Flowlog, you need to make sure that the flow rules that get inserted actually send the appropriate packets up so that those rules can be triggered by the process that you just saw. Our stateful proactive compiler handles all of that automatically, and the paper describes in detail how it's done. So here's where we were a few minutes ago, writing programs where state updates and installation of forwarding rules are performed separately but are still unavoidably tied together. I said that this led to a few standard bugs. None of these bugs appeared in the set of properties that you saw, though. What may have happened to them? Well, it turns out that with a proper stateful proactive compiler and a tierless runtime, you get guarantees that these bugs can never occur. This is analogous to what you get from garbage collection, right? The runtime does a little bit of extra work, and in exchange you get rich guarantees about the behavior of your system. There are many, many good SDN languages, and I can't do them all justice here today. If you're curious about the landscape, I really encourage you to check out the related work section of our paper. In fact, I encourage you to check out the related work section of our paper even if you're not interested in any of the Flowlog work. Because as you can see, the comparison is actually kind of involved and interesting. There are a lot of different metrics and ways to compare SDN languages. The paper contains this table along with a detailed explanation. So let me sum up. Flowlog is a tierless SDN programming language. That means that state updates and flow table rule installation is all handled automatically without programmer intervention. It has built-in cross-tier verification support, verification over the same abstractions. We've got a Flowlog test bed at Brown, and we use it every day. We've been writing some interesting applications in it, and we found as we write those applications that the built-in verification has really helped us. I invite you to either mail me or download the repo from this site, and Andrew and I are happy to take your questions.
So you said to do this verification took about 30 milliseconds for the NAT one. Is that correct?
So it was about 100 for proving the property and about 30-ish for finding the counterexample.
Yeah. Okay. And you're doing this ahead of time before you even ever run this controller program? Is that correct?
Right. This is at static time.
Okay.
Compile time.
Okay. I just lost my second question. I'll let the other person go.
So what's the current landscape of SDN programming languages? What are people, I was thinking like people are just using C and Java, and you list this long list of languages that I haven't even heard about. Don't take offense. So, yeah, this one. So which one of this is like actually being used out there? And if, oh my God.
Yeah, Andrew, do you want to field that?
Most of these are research languages. NLog, though, we did hear about yesterday from Tito. That's the language they use in the Zero Optimization platform. So that's definitely information. Yeah.
Thank you.
So rather than sending packets up to the controller, another alternative to implementing packet processing might be to use like a middle box. And I'm curious whether you've thought about using Flowlog to program, rather than programming OpenFlow switches, whether you've thought about using it to, for example, program a NAT box or some middle box in the data plane itself.
I haven't given that any thought, but now I will.
Cool.
Thanks.
Okay, I remembered my other question. So you have state that you're inserting in for this NAT example, but sometimes you may be removing state based on if you haven't seen some packets over some amount of time, and that's going to happen at the switch and not at the controller. So can you run into a case of inconsistency between what your controller thinks exists in the switches versus what the switches are doing to remove state?
So in this particular program, we are not allowing connections to expire through lack of use. We're currently adding exchanges to the extensions to the language to allow us to express things like that, saying that maybe this forwarding behavior will time out, and on that timeout, the program will receive an event, and then you can delete things from the state.
Okay, great. Okay, thanks.
Thanks.
Oh, no, I'm not done. Sorry. Can you go to slide 24? So, yeah, so actually I'm very curious to hear how your compiler works. So can you sort of, you glossed over this in the talk and I didn't get the chance to look at your paper, but can you walk us through, what is it that it's doing? Is it limited in some way? Can it handle all, types of consistency semantics the applications may want for the kind of updates that may be happening in the data plane?
Sure. So there are some things that the language supports and that the language doesn't, and there are some things the compiler supports and that the compiler doesn't. I just mentioned something the language doesn't support, right? The compiler works by, let me go to an example. Right. You have these rules, and anytime you have a forwarding rule or a state update rule, the compiler looks at those and then goes and replaces references to state with the current state of that database table. So we do partial evaluation. We go in and we take a stateful program and then we create a temporary stateless program that's true for the current state. And then it's a trivial syntactic manipulation to produce netcore. And then we use netcore as a proactive compiler.
I think that's fine. I mean, I guess where I was going with this question was that I was wondering if this is too high level an abstraction, such that it's actually preventing you from doing things that may be useful. For example, if you look at the Swan paper and they have these notions of different sort of congestion-free updates and they want to stage updates in a certain way, and I can't quite wrap my head around how that could be done in Flowlog. Can you comment on that?
Yeah, so the crux of your question is really that there are some parts of the policy. What? You got it. The crux of your question is that there are some parts of the policy that you might want to care about sort of on a switch-by-switch basis, and the policies we've presented here are treating the network as sort of a one big switch, right? Like that everything takes place centralized. That's the abstraction that Netcore introduced, and we've carried on using that because it made it a lot easier to do this work. I'm very much interested in things like the Z update method and the Swan update method, and I think we'll have to think more about how to fit them in, but it's going to take a little more work. So yeah, does that answer?
Hi, this is not my field, so this might be completely stupid, but this resembles very much Erlang with pattern matching, and which is also invented for switching and network processing. Have you guys studied the similarity of using a functional language like Erlang instead of a SQL-inspired domain-specific language?
So I think we're inspired by Erlang, although I'm only familiar with it at a very shallow level as well. So I don't know if I can say more about that.
Some of those other languages do use a more functional style, so you can look at them if you like.
Okay, let's thank Tim and Andrew.